Well, hello everyone. Welcome to Did You Know, the ESCO HVAC show. There is a lot of talk about refrigerants right now, and we're here to help you understand all of these differences in refrigerants and how they impact you when we're actually out in the field using gauges to take temperature and pressure readings and set superheat and subcooling charges. And we really need to understand the chemistry behind these refrigerants. Did you know that all 400 and 500 series refrigerants are blends of other chemicals or refrigerants? I know, maybe we haven't been told that before. Even refrigerants like our R410A, R404, 409, 407, 500, 502, they're different blends of refrigerants. Sometimes they like each other, sometimes they don't. So that's what we're going to do. We're going to do some experimenting right here in the ESCO lab to help you understand what blended refrigerants look like, to understand what is glide and what is fractionation. Are you ready? Oh yeah! Okay. So let's talk a little bit about glide. Not everyone understands what glide is. It's actually pretty simple. If we take two different chemicals that have different boiling points and we mix them together, either they are going to really like each other and they're going to have a new boiling point that is very consistent with whatever pressure it's at, or the two different chemicals are going to boil off separately. And that's what we find in the 400 series refrigerants. The 500, they like each other. I can take two different chemicals with two different boiling points, mix them together, and they are happy as can be. And so when we look at our PT chart, there's only one number that we reference because those two different boiling points have now came together and has a new common boiling point. But our 400 series refrigerants, it's not really like that, right? So let's do a little experiment. Let's take two different chemicals with very different boiling points. We're going to start with plain old water, and let's give it some color so we can actually see that it's going to be separate from the other one we're going to put in. Right? Okay, so let's give our water just a little bit of color. We're just going to pick on blue. Oh, that's some ugly looking dye. Ooh, isn't that cool? Right? Let's mix her up a little bit too, so that we get it all one consistent color. Now, we've added dye, which has a very high boiling point, so it's not really going to affect our different chemistry. We're just using the dye to show that we have two separate chemicals. Well, what happens if we take water that has a boiling point, and then we take another chemical that has a very different boiling point? This time we're going to pick on ethanol, alcohol, right? This particular one of choice is just clear tequila, right? So we're going to mix in some clear tequila, and if they like each other, they're going to be an azeotropic chemical, which means their two boiling points, even though they were separate, now have a new common boiling point, and they like each other. Well, what happens if they don't like each other and they just kind of live with each other? They deal with their differences. Well, that's where we have our zeotropic or non-azeotropic. That means they're going to be together, but not necessarily happy about it. And so they're going to boil off at different points. Okay, so we got our blend. We now have a new chemical. Well, that's kind of fun. I'm going to just leave that spinning just for the heck of it, right? Isn't that cool? Now we're going to add some heat to it, and we're going to see if we can separate these two different chemicals which have separate boiling points. One boiling point for water at atmospheric pressure and one boiling point for our ethanol at atmospheric pressure. So we're going to apply some heat to it, and we're going to give it just a little bit, and we're going to see if we separate the two of them. So that distance in between where one chemical starts boiling and then the temperature that the other chemical starts boiling, That window is called our glide. And it's the same way when we're coming back down, when we're condensing from vapor to liquid. One is going to condense before the other, and it creates a window in our glide. It's in that window that we worry about fractionation. Fractionation is simply the ability for our chemicals to separate while they're in that window. Meaning that if we had a leak and it was in the right spot, the right location in that point of our system, then we could actually lose one chemical in vapor form and the other would not be boiling yet. So if we were traveling on a pipe and we had liquid in the bottom and vapor at the top, but only one of our chemicals had started boiling, that means all the vapor on top is from our one chemical. And so there's the potential for fractionation. So we just have to be aware that all of our 400 series refrigerants and 500 series refrigerants have that potential. That's why we charge them with the can upside down, so that we are only putting liquid into the system just in case they happen to be different inside of our tank. So learning that glide and fractionation happens in that window in between the two boiling points is very important when we're setting superheat and subcooling of our chemicals. All right, let's see if we can get this bad boy to fractionate. So what we're seeing now is as our chemicals are sitting here mixing, we don't have to mix them, but it looks pretty cool. We're applying heat so that we can raise the boiling point of our two different chemicals. And the goal is to be able to heat our ethanol up to the point that it boils, evaporates before our water does. If that happens, our ethanol is going to boil off into vapor form, and it's going to hopefully condense back down into our other container here so that we're actually separating the two chemicals. It's going to take a little bit of time as we raise this temperature, but we should start seeing that, and we should see the ethanol boil off before the water. It's pretty cool. Oh yeah, we're cooking now. So we are boiling off our chemicals. And as you can see, one of our chemicals is already condensing back down into a liquid over here. Now, which liquid is it? Is it ethanol or is it H2O, our water? So we're going to let this run for a little while and we're going to find out. And then we're going to see if we have boiled off our ethanol and left our water, which means we approached the boiling point of our ethanol before the boiling point of our water, and we removed ethanol out in vapor form without removing the water. That's pretty cool. Okay, now that we're starting to boil off, let's monitor the temperature of our boiling and see what we have. See if we're actually boiling at 212 or if we're boiling less than that, like at the boiling point of ethanol. So we'll just add a simple K-type thermocouple. We'll put it on our boiling line. See if we can monitor this bad boy. I'm smelling a very familiar aroma. Smells like tequila. Okay, isn't this exciting? We're actually seeing it in action. Well, what are we actually seeing? Well, we're seeing that our ethanol actually has a boiling point of around 173 degrees Fahrenheit, whereas our water has a boiling point around 212. So the distance between our 173 and our 212 is our glide. We've actually been very successful at boiling off our ethanol out of our new mixture and leaving primarily water. You can see we got a few little bubbles of ethanol boiling off here, and we've lost a little bit due to just vapor, but I wanted to make sure that we were in atmospheric pressure during this whole experiment. And you can see we've actually got a pretty decent amount of our original ethanol in the container. So we're going to shut this down. It's been running for about a half of an hour or so. So we've been boiling out our ethanol along the way. Hopefully that's exactly what it is. So we're going to shut it off. We're going to allow everything to cool down. And then we are going to see if we have water and ethanol, or tequila. All right, see you in a minute. All right, are we ready to see what we've got? Oh yeah, I am. So let's do a quick recap, right? So we have learned that glide is the distance between the points at which our chemicals boil or condense, right? It's that window in between their boiling points. And it creates a place that has two different points. It has the bottom, which we're going to call the bubble, and it creates the top that we're going to call the dew. So we know that in the middle, we can have a combination of chemicals that are, in a different state. So anything above the dew is going to be vapor. So that's what we use for calculating superheat. And then down at our bubble, we know that everything below that is liquid. And so we use that when we're calculating our subcooling. So I hope you see that we have two different boiling points. At atmospheric pressure, we had water that would boil at 212. We had our ethanol that would boil at around 173, which means we had like a 39-degree glide between those two. So the thing that we have to be concerned with is fractionation, because we do have that potential in certain scenarios in that glide window. If say we had a leak and we were leaking vapor out. If we were in the middle of that glide, we have the potential to leak one of our chemicals and not the other. Now, most of our manufacturers will tell us that even chemicals like R451B, which is going to be one of our new refrigerants in place of R410A on new equipment, it has a glide of a couple of degrees. And we're being told that it's not significant enough to need to replace all of the refrigerant unless it has been leaking for a very extended period of time. As you can see, even in this little experiment, it took a half an hour, 40 minutes just to be able to remove that small amount of ethanol. So we're not as concerned. We had between 0.2 of a degree and maybe 5 or 6/10 of a degree of a glide on R410A, because R410A had two different chemicals, R32 and R125. So we can see that in that glide, we have the potential for fractionation or fractionization, depending on how you hear it, and we can end up separating a chemical. So, are we ready to see? Did we actually separate our one chemical and not the other? Did we separate ethanol from water? Well, there's only one way to find out. We've had a little bit of time for it to cool down. Let's see if we have water or tequila. Definitely not water. So there you go. The fundamentals of glide, where we have a bubble point and a dew point, and we have a potential for fractionation or separation of our chemicals in between. So be aware that best practices would say if we have a leak in the vapor portion of our system and we're not 100% sure did we have fractionation, it's always best practices to replace refrigerant and add new. But our manufacturers are telling us that chemicals like R454B don't have a wide enough of a glide to contribute to excess fractionation. Some of our refrigerants out there, say like our 409, 407, 414, some of those had very wide glides, sometimes as much as 10 to 14 degrees. Those we definitely had a concern with. So going forward, we can see that we weren't very concerned about it with R410A, but we still inverted the jug to make sure that we got liquid refrigerant into our system. With R32, it is a single component refrigerant. Doesn't matter if the jug is vertical or if it is flipped upside down. Our R454B, since it is a blended refrigerant, it will have R32 and 1234YF. it really should be inverted, just like we did with the R410A can, so we make sure that we get liquid from the bottom of the tank and not potentially vapor that could be mixed. Fractionation in the top. Thanks for joining us. All right, we have time for one additional lab experiment. You may not hear about this much in the HVAC refrigeration training, but when we're talking about chemicals, there's another fun little attribute that I always like to discuss. It's called sublimation. So we've talked about going from a liquid to a vapor, but what happens if we go from a solid to a vapor? Can we actually do that? Can we skip the liquid phase? We actually can if it's a drastic enough occurrence in a short period of time. That's what we're actually doing when we're working with our dry ice mixed with water. So if we take a look at this dry ice in our solution of water with a little bit of coloring, we can see that we truly are going from a solid directly into a vapor. We're boiling off past the liquid phase. We're changing phases so fast, we do not stay in the liquid phase. Straight from solid to vapor. And it's those vapor gases that causes the fog that we see. That's little small particulates of moisture, of water, that enters into the air. But it happens because we were boiling our solid. Kind of interesting, isn't it? So sublimation is the act of going directly from the state of solid to the state of vapor or gas. It's very intriguing to watch.